One project that I'm working on is actually very, very easy to describe. It goes back, I should know this, but maybe 200 years or something like that, which is what is the minimal area problem? So this is a very, very old problem. Imagine you have some piece of wire and you dip it in soap, and then you take the piece of wire out, like a circle or a square, any shape, and there is a surface, a soap bubble surface, that's the surface with the minimal area. So a very basic question in mathematics is, what is the minimal area for a given shape? So if I have a circle, if it's a plane, the surface is just flat. But if I have a complicated shape, the surface is going to be very complicated. So one thing I'm trying to understand, so of course this is, as I said, a very, very well posed problem. Actually, mathematicians work on this problem, trying to understand, are we certain that such surface exists? When does such surface exist? In which dimensions do such surfaces exist? And so on. But physicists also care about such problems. They appear when we study, well, soap bubbles, for example, but also string theory, because string theory describes surfaces, which are strings moving in space, time, and so on. So it's a problem that is relevant all the way from string theory to soap bubbles. And so I'm trying to understand that problem. And in particular, I'm trying to understand how can we study areas of minimal surface, what's the surface, what's the area of these minimal surfaces without knowing the shape of the minimal surface. Because often knowing the shape of the minimal surface is too complicated. I mean, if you give me some polygon wire that is very complicated, there's not too much hope that I'm going to find the shape. What about finding just the area? You tell me I want to find the optimal surface that ends on some pentagon or hexagon that's all twisted in space. And you ask me, please give me the area. I think it should be possible to compute this area without knowing the shape. So that's something I'm very much actively working on with some colleagues. So that's one problem that, as you see, it's very easy to state. You can say it's a problem either in mathematics or in physics. Maybe I'll stop here and see if you have any questions or if you
Sure.
want to go on. I
Uh,
have many projects, of course. So this is one of them. It's the one I worked on yesterday and that I'm going to work on today. So it's probably the one freshest in my
right.
mind.
I mean, so this problem, as you said, that it's quite easy to explain what the problem is. And someone, someone who is relatively familiar with how physics and maths works would tend to guess that there must be some significant progress that has already been made on this problem. So, how much progress has been made on this problem already?
Uh, so uh, So there are many approaches to this problem. One, as I said, the idea is find the minimal, the surface with the minimal area, the optimal surface. So this is a field of mathematics called calculus and variational principles that's very well studied. It's a field that was developed since Lagrange, trying to understand what equations describe optimal things, be it the movement of particles or shapes of minimal surfaces like I described. So this is very well understood. And indeed, one of the ways of studying this problem is solving so-called differential equations. So equations that give us the shape of these surfaces. These are equations which are a bit different from differential equations giving movement of bodies, because movement of bodies, typically we specify the initial conditions. I throw a rock and I say, what's the initial position and velocity? And then I evolve this differential equation to find out the shape of the particles. Or when I study cosmology, I give the initial conditions for the universe and let it evolve, and I study the differential equations that govern the size of the universe. Here, when finding the surfaces of soap bubble, we don't give initial velocities, but we give what we call boundary conditions, global boundary conditions. We say, what is the shape all around the surface? We say, where's the wire? And then we evolve the equations, if you want, inwards, and we find the optimal shape that goes inside that fills in this wire. So that I would say is the brute force way of doing it. You give me some piece of wire and I just compute it. I either dip the wire in soap and take it out and measure, or in the computer, I optimize solving these differential equations by what is called relaxation, which is you start with some wrong guess and let the computer get a better and better and better guess until you get the optimal surface. Now, this is one way. And for me, it's like the lab, is that whatever method I'm going to come up next, I have to contrast it with this. I'm going to produce new ways of computing, and then I always have to check. If I say, oh, I have a better way of computing, great. So compute it by brute force first, get a number, 4.23. Does your new method give 4.23? Good. So what would be new methods? One is sometimes you can find these surfaces analytically. If you are lucky enough, if your boundary conditions are simple enough, perhaps you can just solve the differential equations. You don't need a computer. You just solve it with pen and paper. Such examples were done. There is a very famous polygon known as the Schwarz quadrilateral. That was solved in the beginning of this minimal surface problem. It's a particular shape with 4 edges that is very symmetric, and then you could solve exactly the shape of this surface. There is some funny square root with 8 zeros, and you integrate that square root or inverse square root, and you get the shape of this surface. Recently, people in the study of ADS-CFT, that I'm sure it's a topic we are going to cover at some point today, which are these dualities between gravity and quantum mechanics, people like Aldai and Maldacena, they understood that such surfaces also appear when studying the scattering of gluons. Okay, the analog of photons for the strong force. And these gluons, it turns out that studying the scattering of these gluons is also related to a minimal area problem. Namely, when you study the scattering of gluons in the so-called strong coupling regime, the regime where quantum effects are very strong in these ADS-CFT scenarios, you have, if you want to study, like, for example, 4 gluons, 2 gluons coming in the past, 2 gluons going out in the future, you also need to consider a quadrilateral, but it's a quadrilateral where the wire is put at the boundary of this spacetime, very far away at this boundary of this anti-de Sitter spacetime. So here you have 2 examples, the Schwarz quadrilateral, studied maybe in 18 something, I don't know. And then the Aldai-Maldacena quadrilateral, the quadrilateral that is at the boundary of ADS and whose minimal surface computes this scattering amplitude for gluons. And now if you ask, can I take these quadrilaterals that are known analytically, and can I find not only quadrilateral, but any polygon, and not only at the boundary of ADS, and not only in flat space, but all the way in between? Can I find what's the minimal area of any polygon? And the answer is we don't know how to do it. This has not been done. But what we are trying to explore is the notion that these surfaces that often I think of them as strings because they are really like the shape of a string moving in space-time draws some surface, are integrable. That means that their dynamics is exactly solvable. You can imagine that this surface is like some piece of material, and the ripples, the waves, the fluctuations of this surface are integrable. And that is very powerful. It means that when you change the shape of this surface, there are lots of symmetries and lots of conserved charges. These ripples propagate and they move around on this material, but they don't move around in a random way. They move around in a very organized way. And it's this power of integrability that I'm trying to tame in order to compute these general polygons for any number in a very generic sense. In the context of gluons, we had done this before in the past, maybe 10 years ago, with Fernando, Juan Maldacena, Gaiotto, Amit Sever. I had studied this problem of trying to understand these polygons in that particular context of polygons that end on the boundary of anti-de Sitter. And that's exactly what we did. We managed in that, like this 10 years ago, to compute the area of these polygons without knowing their shape. But as I said, it's for very special polygons. It's polygons that end on the boundary of this anti-de Sitter space. So I was thinking, I want to study this much more generally. I want to understand much more how to understand areas of surfaces without seeing the surfaces.
I see. So, for example, if we look at the diagrams that are behind you, are they related to 4-gluon exchange or something else?
This diagrams there. Yeah, so what they are. In short, they are. But in detail, the way it works is the following. So when you have these surfaces, it seems to be the case that studying a general surface, imagine you have some surface that's very complicated. It's topology can be very complicated. So here in the back, I have some examples where I have like two strings moving in, they interact and they split. So it's like a topology of two pair of pants that are glued together. Now, studying pair of pants that are glued together, there are a lot of parameters. They can be fat, thin, twisted, not twisted. It's very complicated. The geometry of these surfaces can be very intricate. So it seems to be very convenient to break it apart, to cut this surface into smaller building blocks. And it seems like the building blocks that we want to cut this surface in are hexagons or triangles. And well, hexagons are not triangles, so it might seem strange why I'm saying hexagons or triangles. So let's just say hexagons. So if you look in the back here where I'm pointing, you can see that there is an hexagon here. If you count one edge, two edges, three edges, and if you count the other three, it's six edges. So it turns out that if you have some surface, you can somehow always cut it, these string interactions, into hexagons. So it seems like perhaps a way of studying this problem is understanding better these hexagons and how to compute them and glue them together. And this could give us a new way of thinking about this surface. But that's a very technical point, though, if we can go there if you want. But
So if you like this video, give it a thumbs up and consider subscribing, and the YouTube algorithm thinks that you will also like this video.